Buenas tardes. Antes que nada debo decir que estoy muy contento de estar de nuevo en Almería. Siempre estoy contento de estar en Almería. Y ni siquiera hace falta el aplauso para hacerme muy contento de estar en Almería, porque el calor de la gente es tan evidente que no hace falta más, se siente desde aquí. Es un enorme honor y un placer de presentar ahora a Brian Schmidt. Brian Schmidt es norteamericano, estadounidense de nacimiento, vivió en Montana y en Alaska en su juventud. Su padre era biólogo y él dice que no sabía que iba a ser astrónomo. Poco a poco se iba interesando más, pero no era una casualidad que llegó a ser astrónomo. Sin embargo, no era uno de esos casos donde desde pequeño se había interesado solamente por la astronomía, porque ese tipo de persona que se interesa por todo, muchas cosas, no voy a entrar en detalle. Pero lo que ha marcado su vida profesional fue el descubrimiento de las leyes que gobiernan la expansión del universo, o una de las leyes de facto, no la ley teórica, porque vas a oír su descripción del experimento que descubrió la aceleración del universo y la presencia de energía oscura. Tuvo la fortuna de conocer a una australiana, casarse con ella, emigró a Australia y en Australia ha vivido experiencias muy importantes porque, entre otras cosas, ha sido el canciller, que es el rector de la Universidad Nacional de Australia durante 8 años, y ha desempeñado muchos papeles oficiales como asesor al gobierno australiano. Pero más que eso también es un gran experto y abogado en favor de la enseñanza pública a todos los niveles. Incluso ha donado dinero personal a varios aspectos de la enseñanza pública. Y eso nota qué tipo de persona es. No voy a ocupar más tiempo porque podría pasar la hora explicando y describiendo sus logros. Aquí paro y dejo a Brian Schmidt hablar del universo en aceleración. Brian.
Thank you, John. And it is great to be here for my first time in Almería, and a beautiful city. And it is great to be in this historic theater. It's unlike anything I think I've ever been in, so it's wonderful. So I'm going to try to tell a story today about the accelerating universe, and to understand that, I'm going to have to tell you the entire story of the universe from beginning to end. So let's start with the beginning. So long ago, before there were galaxies, something happened. The universe was suddenly expanding in all directions. It was hot. And as it expanded, it cooled. We call this the Big Bang. Now, We don't know what the Big Bang was. We certainly don't know what came before the Big Bang. But we know that something happened about 14 billion years ago, a little less, where the universe was created as we know it, and we can see back to just a few seconds after that in various ways.
Va a hablar del universo, la parte del universo que ocurrió mucho antes de las estrellas y las galaxias, un evento, el evento, el origen del universo tal y como lo conocemos. Este evento ocurrió en una expansión muy rápida, que sabemos que ocurrió. No sabemos muchos detalles, pero no sabemos desde luego lo que podía haber ocurrido antes, pero sí sabemos que nuestro universo empezó así y que podemos medir sus propiedades.
So the first easiest place to see the Big Bang is the image on the screen. This is known as the cosmic microwave background, and it shows the universe 380,000 years after the Big Bang, when the entire universe was about as hot as the sun. And this is a picture of the entire sky looked at microwaves, like the same things that you use to heat up your vegetables in an oven. So that is an image that we'll talk about a fair bit, but it is the first thing that we can see after the Big Bang. Now, to understand the universe, we have to observe it. And those observations really started about 100 years ago. Here we see Hubble, who had access to the largest telescope in the world, a 100-inch telescope. So smaller than the one just outside of town here at Palo Alto, but not that much smaller. And he was the person who was able to go out and start making measurements of the universe.
Para entender la expansión del universo, cuanto más hacia atrás podemos medir, más interesante, y esta es la imagen primero era todo el cielo en microondas, que se llama el fondo cósmico de microondas, que es un mapa del universo 380.000 años después del Big Bang, cuando todo el universo tenía temperatura similar a la superficie del Sol. La expansión misma se descubrió por Edwin Hubble utilizando las galaxias. Eso es como sabemos que las galaxias se huyen y hay expansión.
So Hubble was able to go through and use, for example, how far a star, was able to measure the distance to a star by how bright it appeared. The fainter the star, the further in distance. He just had to assume that the stars near and far were more or less the same intrinsic wattage, same intrinsic power. So he used this idea that further is fainter to measure distance. And then he used another physical trick, which was when galaxies move towards you or move away from you, their light is shifted red if they're moving away, or shifted blue if they're coming towards. We call that the Doppler shift, and it is used for example, weather storms, but also if they want to see how fast you're going on the road if you're a police officer.
Pues para medir las propiedades de la expansión del universo, Hubble tenía que medir dos cosas. Uno es poder saber la distancia de algo y el otro su velocidad. La distancia se mide si tienes un objeto, que puede ser una lámpara, con conocido potencia, entonces si tú mides la potencia que recibes en tu telescopio, sabes la distancia automáticamente. Cuanto más lejos, menos recibes y puedes calibrarlo. Y en términos de velocidad, son los espectros que se mueven al rojo, cuanto más rápidamente, más al rojo. Y si llegan hacia nosotros, al azul. Y eso también se puede usar para medir el universo.
So in 1929, he showed the world his measurements, shown here. And we have brighter stars, nearby objects, fainter stars, distant objects, and then how much the light had been redshifted or blue shifted. And it had been known that all of the galaxies in the universe seemed to be moving away from us. That was a big mystery, which he solved by making this plot, because you can see as you go further and further away, you move faster and faster. The further, the faster. And from this, Hubble told the world the universe is expanding. Now, here's a cartoon. You will notice I have expanded the universe. And if I overlap before and after, when I've expanded the universe, what do I see? I see nearby objects. They've only moved a little bit. If I was measuring their movement, they would be moving slowly. Distant objects, on the other hand, well, they've moved a lot. So, just like Hubble, if the universe is expanding, the further away something is, the faster it will be moving away from us.
Lo que Hubble encontró era lo siguiente, que él encontró que las cosas más débiles, menos brillantes, tienen velocidades más altas. Y eso significa que cuanto más lejos, más rápido. Y eso es característica de un objeto o un sistema donde todo está en expansión, todo. Y entonces, cuanto más la distancia entre los objetos, más rápidamente se separan. Eso es lo que encontró Hubble.
So, I want us to do another thought experiment. The universe is expanding. Let's think what happened in the past. In the past, the universe will be getting closer and closer and closer together until everything is on top of everything else. So the Big Bang naturally occurs sometime in the past if the universe is expanding now. Expanding now, we look in the past, and it's all in one place. So the Big Bang is a natural occurrence in an expanding universe. And graphically, we can think of it like this. Time of Big Bang, the universe expands. Two galaxies get further and further apart. So if I can measure how fast the universe is expanding, and that's the steepness of this line, I can run the universe in reverse and figure out how old it is. Measuring the Hubble constant tells you how old the universe is.
Y entonces, lo que se puede hacer es lo siguiente: si tienes el universo en expansión, mentalmente pones todo al revés y estimas cuánto tiempo se necesita para todo convergerse en un punto. Y eso es natural de pensar que es así. Y este tiempo que calculas es la edad del universo. Midiendo las separaciones y las velocidades, mides la edad del universo.
So I thought this was a great thing to do, and here I am in 1993 at the end of my PhD with my PhD supervisor, and I have measured the expansion rate of the universe. That was my PhD thesis. And what I determined was the steepness of that line. We call that the Hubble constant. It's essentially a galaxy's distance divided by its velocity, and I found that the universe was about 14 billion years old, and we'll go from there.
Bueno, entra Brian en el tema, había gente midiendo estas cosas. Brian empezó en 1993 con su doctorado y él obtuvo medidas de distancias bastante más distantes que antes, porque utilizó mejores instrumentos y más empeño, y él pudo describir que el universo tenía una edad de 15.000 millones de años utilizando este método.
Yes. So many people were measuring this value, and it turned out this is about right, but I was one of many people working on this. Now, this is not just a cartoon. It's actually all tied together by Einstein's theory of general relativity, his theory of gravity. And in 1907, Einstein had what he described as a most wonderful thought. He also supposedly, I'm not sure this is true, had it when he saw a person fall off a house. And as they fell to presumably their demise, the person, he thought, they must feel weightlessness. That is, the acceleration must be directly countered by gravity. And so those things he thought must always be equivalent. And that little thought, it turns out, took him 8 years to go through and eventually write down the theory, which is very complicated. And that theory, it turns out, basically says that gravity and acceleration are the same. They're no different. You can't tell the difference between the two. And as I said, his theory of gravity was published in 1915, and it predicted many things, including that space would be curved. And that curvature of space was seen in an eclipse in 1919, and more or less showed that the universe was as he predicted it, that space was curved, because the sun curves space just a little bit, and during an eclipse, the stars are in different places when the sun is in front than a couple months later when the sun is no longer there and we can see where the stars are.
En 1907, Einstein tenía una idea, una de sus muchas ideas brillantes. Según el posible mito, vio una persona caer desde un edificio. Probablemente murió, pero Einstein se dio cuenta que al acelerar no tenía peso, que la aceleración de la gravedad era básicamente lo mismo. Y de este germen de idea desarrolló su teoría de relatividad general, que explica la forma de actuar de la gravedad en el universo. Le publicó en 1915. En 1919, esto se comprobó, la curvatura del espacio predicho por la teoría, por el movimiento de la imagen de una estrella al lado del Sol eclipsado. Esto yo voy a hablar cuando hablo de los eclipses. Entonces, si quieres realmente aprender de eso, hay que venir el jueves.
You're freelancing. You're freelancing. My Spanish is not good, but he's freelancing. Okay. So, this theory of gravity allowed Einstein to do all sorts of things. One of the things it allowed him to do was to understand how the universe works with gravity. Because it turns out Newton's laws of gravity don't allow you to think about the universe. They break. And this drove Newton nuts. Newton was already pretty crazy, but he could not figure out how you could go through and understand a giant universe. His equations basically only worked if the universe had nothing in it. That was, he could show the only solution. So that was problematic. And so for Einstein, he started working with this, but he got a nasty surprise. His equations said the universe should always be in motion. And in 1916, when he was doing this, he looked around and he said, the universe is not in motion. And then he thought, I've missed part of my equations. There is something called the cosmological constant. This is energy that is part of space itself. And it turns out it makes gravity push rather than pull. And so his idea is, I'm going to have just enough of this to balance out our gravity, and the universe would be static, that it would be not moving. Turns out it doesn't work because it suffers from the butterfly effect, which is if a butterfly in Spain flaps its wings, the whole universe from here to the other side gets put into motion. It is unstable, so it did not work.
Okay. La teoría de Einstein, él tuvo dificultades para aplicarla a todo el universo. Sabía que se podía aplicar localmente, pero su teoría en estado puro, inicial, solamente funciona en un universo sin materia, porque si no, tenía que moverse o expandirse o entrar en colapso. Y el conocimiento entonces fue que no está en expansión. Entonces él inventó un término constante cosmológico para parar todo, para contrarrestar la gravedad, energía embebida en el espacio. Pero, como dijo Brian, eso no hubiera funcionado correctamente por la naturaleza fluctuante de todo, que hubiera destruido.
So Einstein's theory of gravity actually said the universe should be in motion. It should be expanding. And furthermore, it told us that gravity would actually change the expansion. So this diagram I showed you is only correct if the universe has nothing in it. So if the universe has some gravity in it, you and me, our gravity will slow it down. So the universe will slow down over time, and you can note that the age of the universe is less than what you measure just assuming it's doing nothing. Now, in fact, depending on how much gravity, how much stuff there is in the universe can slow down a little bit or it can slow down a lot. And this has effects for the future, because if the universe is empty or very, very light, the universe just keeps expanding forever. But if the universe is heavy, heavier than a certain amount, the universe will slow down, stop, go in reverse, and end in what we like to call the Gnab-Gib, which is the Big Bang backwards.
So, entonces, el problema es que los modelos basados en relatividad general, que tienen materia también, más realistas, tienen este problema. Tienes expansión y tienes gravedad. Si la gravedad es fuerte, es decir, si hay mucha materia, todo se va a parar. Si es poca, a pesar de la gravedad, va a seguir en expansión para siempre, aunque cada vez más lento. Si hay mucho, se va a parar. Si hay suficiente, se va a parar y se va a recaer a un punto, o por lo menos a concentrarse. Eso se llama, al revés en inglés, Big Bang, que no puedo pronunciarlo, pero se dice Big Crunch también.
All right, I'm about ready to get a new translator here. Okay. Now, I told you that general relativity, Einstein's theory said space is curved. This is one of the hardest things to get your head around. If the universe is exactly the right heaviness, density, so that the universe slows down and comes to a stop at an infinite time in the future, it turns out it has the geometry of being flat, where triangles add up to 180 degrees. But if the universe is heavier than that, gravity bends space into a sphere of 4 dimensions, not the 2 up here, where if I head out this direction, I eventually would come back to where I am. Space wraps onto itself. Space is finite. Or, if the universe is lighter than that critical amount, space bends away from itself like a hyperbola or a saddle. In this case, the heavy universe, triangles add up to more than 180 degrees. The light universe, triangles add up to less than 180 degrees. So that's how we can measure this if we're very clever. Now, if you were to measure the angles on Earth, not in this room, but let's say you go from Almeria to Canberra, then to Moscow. That triangle on Earth adds up to more than 180 degrees. Try it with a globe and string, because the Earth is curved.
Entonces, los dos tipos de geometría en el espacio pueden ser si la expansión justo sigue para siempre, eso se llama plano, el universo plano. Si hay un triángulo en este universo, los ángulos miden 180 grados. Si es muy liviano y no llega a pararse, los ángulos miden menos. Y si es en colapso, esferoidal o esférico, entonces los ángulos miden más, como en la superficie de la Tierra. La Tierra no es plano, es esferoidal, entonces los ángulos son más de 180 grados. Y si sabes medir todos los parámetros bien, puedes intentar distinguir entre estos modelos de universo.
All right, so I have finished my PhD thesis in 1993, and we have just developed big digital cameras for the first time. We had the opportunity to go through and do an experiment that would allow us to measure how the universe changes its rate of expansion over time. So, if the universe is empty, it just stays at the same rate. That straight line. That's a light universe. Doesn't slow down. If the universe is flat, perfectly balanced, then it goes on this dotted yellow line. If you're on this side, bottom of the line, then gravity wins. The universe is finite, and the universe will eventually stop expanding and go in reverse. If you're above that line, gravity loses. The universe expands forever. The universe is infinite and curves away from itself. Now, to do this, as I said, we need to look back billions of years. When we look back billions of years, we do that by looking very, very far away, because light travels 300,000 kilometers per second. And so if I look far enough away, I can see places where light has literally taken us 5, 6, or 7 billion years to reach us. So I'm actually looking in the past by looking far away. And to do this, we needed something like Hubble had, but we needed something better than Hubble had. And the thing that was also appearing in 1993, 1994 were cosmic explosions called Type 1a supernovae. These explosions take 20 days to reach a brightness which is 5 billion times brighter than our sun. These are the objects that make the iron in the chairs you are sitting in. These objects, it turns out, can be used to measure distances to about 7% per object. Now, 7% is not great by your standards, but by astronomy standards, which were used to factors of 2, this was amazing. And because they're so bright, we can see them, it turns out, with these new digital cameras 5, 6, or 7 billion years away. So that's what I saw happening in 1994, just after I finished my PhD. And I brought together a whole bunch of people, my friends, to do this experiment.
Pues después de terminar su tesis en 1993, dos cosas. Por un lado, había detectores digitales de los más modernos introduciéndose y se descubrió un nuevo un tipo de fuente muy brillante. Es muy importante que necesitas una fuente muy brillante por la enorme distancia que tienes que observar. Y estas supernovas tipo 1A son los equivalentes de 5.000 millones, no billones a propósito, 1.000 millones de veces la luminosidad del Sol en un objeto. Y tienen buen comportamiento que durante 20 días se aumentan su luminosidad, llegan a un pico que se puede medir y entonces son ideales para hacer, como se llaman, velas estándar o candelas estándar para medir estas distancias y intentar explorar los modelos. Él organizó un grupo para hacerlo.
And these supernovae were understood. All that work actually took place in Spanish, but in Chile, by my colleagues. And here are a couple of them. Nick Sunseth here at Cerro Tololo is who helped start the big program that we used to look back in time. And it was hard because Type 1a supernovae are very rare. The last one seen in the Milky Way was in 1604, and it was, cataloged by Kepler and Galileo. We have not seen one since. So in order to find one, you have to look at thousands upon thousands of galaxies so that you can, in any given week or two, see the exploding star. That means we have to look at very large parts of the sky to see enough galaxies, and that's why we needed these large digital cameras, which had not existed before. So, finding the supernovae, we had these big digital cameras, which were roughly, we were using 8 megapixels. So, it doesn't sound that big, but it was big back then. But remember that I had a 1 gigabyte hard drive. That was the biggest thing available. And I had computers that were much slower than my iPhone. And I would take 50 gigabytes of data, so about 1,500 images like this. And there would be on average 3 supernovae. So I had to find the needle in the haystack, and here is the object. And the way that we found these was using image subtraction. So I had to take an image, and I had to make it look exactly like the other image. Then I subtracted it, and anything that changed, those are the things we were interested in. Now it turns out that's the software I had to write, but no one had done this before, so we had to kind of make all those things up. That was the hard part.
So el proyecto era un proyecto masivo, porque una supernova de tipo 1A ocurre en una galaxia cada varios centenares de años. El último en la Vía Láctea ocurrió en 1604, observado por Kepler y Galileo. Entonces, son pocas. Tienen que muestrear miles de galaxias. Necesitas grandes cantidades de datos. Tenían cámara de 8 megapíxeles, que era muy grande entonces. Acumuló en un proyecto 16 gigabytes. Y bueno, los ordenadores eran muy lentos y el proyecto necesitaba no solamente tomar las imágenes, sino como mínimo tomar las imágenes mismo 2 veces para que la supernova aparezca en uno y no en el otro, que es la única forma de buscar. Es un proyecto muy duro.
All right, so what did we find? It took us about 4 years. And in this diagram, I'm going to show you each exploding supernova is a dot. And it has uncertainty done by the lines. Okay? So what you can see is these nearby objects looking back about 1 billion or 2 years in the past. Oops, I've lost something. Oh, I'm gonna have to do it this way, maybe. Nah, well, maybe you can see it. These are the nearby objects. You can't tell they're here, here, or here. These are the distant objects we discovered. You can see that not a single one of these objects is down here where gravity wins. Now, I was kind of sad by that because I kind of liked the idea of a universe that had a beginning and an end. But the universe does not care what I think. It just does what it does. But the more interesting thing is that although these objects, sometimes the uncertainty goes into the yellow bit where gravity loses, on average, they're above the line, where the universe was expanding slower in the past and had sped up. So this data showed that the universe was not slowing down, it was accelerating. And while we were getting this data, another team at Berkeley was doing a similar experiment, and they found exactly the same thing at basically the same time.
El proyecto duró 4 años, el primer proyecto, y los resultados están ahí. Las galaxias las supernovas más cercanas siguen casi la misma línea horizontal, donde la gravedad ni gana ni pierde, pero las más distantes están por encima, y eso significa que al principio la expansión era más lenta, y significa que mientras tanto la expansión se había acelerado, que significa básicamente que algo está conquistando la gravedad y empujando todo aparte. Y no solamente ellos, sino otro grupo en Berkeley hacía un experimento similar con resultados casi idénticos.
So, it is for that reason that we got to, well, it worked that time. Okay, who knows? My slide, for whatever reason, didn't do that the first time. But that is why the two teams were awarded the Nobel Prize. I know the data seems underwhelming, but it told us something profound about the universe. And so here we are, the two teams in Stockholm in 2011. So what does this mean? Well, we have to go back to Einstein's cosmological constant, which we threw away, it turned out, when we realized it didn't really serve any purpose, because it was really the only way we knew how to make the universe speed up. If the universe, it turns out, is full of energy. Now, we don't know it's the cosmological constant, so we give it a generic name called dark energy, because maybe, unlike Einstein's cosmological constant, maybe this changes over time, maybe it doesn't. We'll see. So, I'll let you go there.
Pues entonces habían descubierto algo profundo que cambiaron el interés, la experiencia de toda la comunidad astronómica sobre el comportamiento del universo. Y algo energético estaba impulsando, acelerando la expansión del universo. No sabían si eso era realmente la famosa constante de Einstein, que posiblemente sí, o otra cosa, y todavía eso no se sabe. Pero las medidas son las medidas y son potentes.
Now, one of the reasons why we made our discovery in 1998 and we won the Nobel Prize in 2011 is people, including myself, were not sure if this was right. This was a rather crazy thing to be, and so we needed to look at cosmic acceleration from different ways. And it turns out the cosmic microwave background, the thing that's left over from the Big Bang, is a Rosetta Stone for physics, because every little bump you see there is a sound wave. And sound waves, we understand here on Earth. Now these sound waves in space, and yes, there is sound in space, but the waves have to be very, very long, like bigger than a whale long. They're like light years long. It turns out that those sound waves are left over from the Big Bang. And if you think about the universe as a pond, and you throw a rock in the pond, the waves depend on what the universe is made out of. So if the universe is made of honey, it has different waves than if it's made out of water. And so the Big Bang was like throwing a whole bunch of rocks into the pond. The waves splash around, and then we get a picture of them 380,000 years later. And it turns out we can model that in a computer really, really accurately. Okay? And so this creates, it turns out, one of the most spectacular experiments in cosmology.
Pues, después de descubrir la aceleración, tenían que buscar algo para confirmarlo, ayudar en su entendimiento. Y el experimento que más ayudó era esto, el mapa de las variaciones de temperatura en función de posición medida en el fondo cósmico de microondas. Al principio desde el suelo, pero con gran precisión con el satélite COBE más tarde y después con otros satélites. Y esto siendo Planck. Y eso ofrece el mismo tipo de información como si hechas piedras en un líquido, la forma de todas las ondas que se ven depende de la naturaleza del líquido, sea agua por un lado o miel, por ejemplo. Y entonces eso es un mapa que da mucha información sobre la cosmología.
All right, so the first thing we could measure was how big the sound waves were. Okay? Why does this matter? Because how big and the shape of the universe creates the triangle. Okay? So if the universe is closed onto itself, okay, that means the universe is heavier than the 100% of material to make the universe flat. And it turns out that magnifies, that makes things look big. The triangle has an angle greater than 180 degrees. If the universe is light, less than 100% of that perfect number, then the triangle has less than 180 degrees, and the sound waves are going to appear smaller. And then if the universe is just right, then the triangles have 180 degrees, and they have a size in between that we can calculate from physics. So this is what the universe would look like if it were the three things. And it turns out it is exactly on that amount. It is within 0.1% of the universe being just the right amount of stuff to make the universe have 180-degree triangles.
Well, entonces, se puede aplicar la prueba de los triángulos a los datos en el fondo cósmico de radiación de microondas. Y al aplicarlo, predices la distribución de estos tamaños de objetitos en el microondas. Y comparas tu predicción con las observaciones. La predicción de un modelo abierto donde se supone que el triángulo tendría ángulos, suma de ángulos menor de 180 es esto. El cerrado es esto y el plano es esto. Y resulta que la predicción del universo plano está en buenísimo acuerdo con las medidas, con una discrepancia de menos de 1%.
And there's more, because we get to measure how many sound waves there are of different size. And it turns out there are a lot of sound waves at this size, this size, this size. And it turns out the line that goes through each of those dots is the theory. That was not done afterwards, but done based on our measurement in 1998. Now, in physics, when your line follows your data like that, it usually means one of two things. You really know what you're doing, or you've cheated. Okay? And that line, it turns out, tells us what the universe is made out of. Amongst things. It turns out this is insensitive. It's only insensitive to things that have gravity. And it turns out it tells us the universe is 5% atoms that we're made out of, and 25% something I haven't talked to you about yet. Dark matter. That's stuff that has gravity, just like atoms, but it doesn't interact. It goes right through itself. It goes right through the earth. It goes right through the sun. It goes through everything. It only is something that works by gravity. So if you and I, with atoms, hit each other, we bounce off each other. Dark matter just goes whoosh right through it. It's magical.
Bueno, entonces son una línea y puntos de datos. La línea es la predicción del universo medido por por Brian y sus colegas, un universo con aceleración. Y los puntos son las medidas de los rasgos del fondo cósmico. Y están en gran acuerdo. Entonces, como dijo, si hay un acuerdo tan bueno, o significa que la teoría es válida, o significa que estás haciendo trampas. Y en este caso hay que creerlo, que nadie está haciendo trampas.
I don't know what he just said, but I don't like it. So dark matter, we've seen since the 1930s that wherever we look in the universe, there's more gravity than atoms. And we have called this Dunkelmatter, is how it was first described by a Swiss-American physicist named Fritz Zwicky. Vera Rubin looked at this, my colleague. John knows Ken Freeman looked at this. And now we have a way to measure it very accurately. If dark matter does not exist, you wouldn't see the bumps as we saw them. And we think it might be an undiscovered particle. We have already the neutrino, and the neutrino goes right through the Earth. It goes more or less through the sun. And it turns out the problem is it doesn't have enough mass. We know how many neutrinos there are in the universe. And it's about several hundred times fewer than we need to make up the dark matter. So our thought was maybe there is an undiscovered particle, like the neutrino, that we should look for. Now, we've been looking for it very hard for the last 20 years by putting big vats of xenon, liquid xenon, in mines and waiting for a dark matter particle to just occasionally run into the xenon and make a ping. But at this point, we have many, many years and many, many tons of xenon, and we have 0 pings. So we don't know what dark matter is at this point.
El acuerdo bueno entre los datos de la teoría necesita que la materia en el universo es 5% de materia normal, que se llama bariones, que son protones y neutrones básicamente, y otro 25% de lo que necesita para cerrarlo en materia oscura. Esta materia oscura no es lo mismo que la energía oscura, es materia probablemente de partículas. Y uno de los problemas de la ciencia moderna, física moderna, es encontrar estas partículas de materia oscura. Se mide en las galaxias porque la rotación de las galaxias es mucho más rápido que debe ser si fuera solamente bariones, muchísimo más. Es ampliamente claro que algo falta, mucho falta. Y no pueden ser neutrinos porque sabemos ya el límite de masa del neutrino y la cantidad de neutrinos pululando por el universo. Eso falla por factores de centenares. No sabemos lo que es esta materia oscura. En el experimento que nombró Xenon N, donde se puede intentar detectar una partícula de materia oscura en gran cantidad de líquido, xenón líquido, y nadie lo ha encontrado todavía.
So, let's think what the cosmic microwave background tells us about the dark energy. So, relative to a just right universe, because we know that the universe is perfectly flat. It adds up to 100% because the triangles add up to the 180 degrees. We know that 25% of that is dark matter, this mysterious stuff. 5% is atomic matter. And so there's a missing 70% of mystery matter in this experiment. And it turns out that's the same stuff we need to accelerate the universe. We're seeing it the same thing, just from different ways. So any way we look at it, and it turns out we've looked at it many ways over the last almost 30 years now, we see a picture where 95% of the universe was invisible to us here on Earth. 5% are the atoms that every Nobel Prize, other than my own, has been based on. Ours is the one that's based on the rest of the universe. My hope is someone else will figure out what's going on, and I'll show you our efforts thus far, so someone else will win a Nobel Prize with this stuff.
Lo que dice es que entonces los datos de las galaxias en expansión y los datos del fondo cósmico, geometría, implican un universo plano. Eso es el tema de los triángulos que se han medido. Y para cerrar este universo, hacerlo exactamente plano, tenemos 5% de materia normal, bariónica, 25% de masa oscura y 70% que resulta ser la energía oscura necesaria para acelerar el universo. ¿Qué significa todo eso? Que solo 5% de la masa del universo la conocemos, no sabemos lo que es el resto, son dos tipos de cosas desconocidas. Por un lado es una situación muy insatisfactoria, pero por otro lado es una situación magnífica, porque implica que generaciones de físicos van a tener trabajo. Y él expresó su esperanza de que gente va a ganar un premio Nobel porque lo suyo es el único que se ha ganado basado en el 95%. Los restos, de una forma u otra, se han basado en el 5%. Y él tiene esperanza que alguien o algunos van a llegar y superar el desafío presentado por eso.
So, 27, 28 years later, this is, instead of a handful of supernovae, these are how many supernovae there are. Almost 2,000. Turns out there's more than that. These are really good 2,000. And what you see here is a line. This is the line we put out in 1998. So it looks pretty good. Actually, it almost is embarrassingly good. It probably shouldn't be quite as close as it is. But it turns out it's very difficult to find supernovae here because you have to look at almost the whole sky and they're faint. So we're building new telescopes that can do that. But in this part of the diagram, it turns out the line is a little above. The best fit is a little above. And people get excited when they see that. Maybe the universe is not doing the same thing as Einstein's straight line that we proposed in 1998. I'm not yet convinced, but it's interesting, and we're getting a whole bunch of new data with new telescopes, Vera Rubin, but it turns out the Euclid experiment and the Roman experiment also going up soon. There's also a new way to measure distances, which uses these sound waves, because these sound waves turn out, get imprinted in galaxies. And so if we go out and look at how the galaxies are distributed, and this is real data, it's not fake data, these are the real galaxies measured over the last 5 years with an experiment, you can see the sound waves imprinted in the galaxies. So we can see how big the sound waves were in the past and how big they become over time, and use that as a way of measuring distance. Tied to near the Big Bang, coming this way, rather than us looking at things nearby and comparing far away.
Pues hay un nuevo método que se está aplicando últimamente que usa la distribución de las galaxias en el cielo, que tiene un mapa que no es tan diferente a simple vista de lo del fondo cósmico. Y hay nuevos telescopios que se están usando para hacerlo y que se pueden medir la distribución de las galaxias de la misma forma que en el fondo cósmico. Y los proyectos de Euclid, del telescopio Roman y del Vera Rubin son grandes telescopios diseñados para ir adelante con esto. El problema parece ser que en un rango de distancias el número de supernovas no es lo que parece no ser conforme con la línea recta de Einstein. Y hay mucha controversia sobre esto. Brian dice que no está muy convencido de uno como otro. Es una cuestión abierta. Pero ese es por donde van las cosas.
So, here are the sound waves measured in galaxies that are different distances away. And what they allow us to do is to measure the distances, like supernovae, and very accurately. And here, what I want you to see is the lines lie just a little below the line that we predicted back in 1998. Now, we are unsure how significant that is. Right now, it looks like about a 5% chance of being that big, or 95%, there's a 5% chance it could be that big. And for physics, it's not enough. So we're taking more data, and we will see if that becomes a bigger thing or a smaller thing as we get more data. So we don't know. It's almost exactly like Einstein's cosmological constant, almost. So I don't know. If it's different, that would mean that it's changing. And if it's changing, then we don't know why. And as I'll tell you, I can't make predictions about the future unless I understand things really, really well.
Pues este método, utilizando lo que se llaman las ondas de sonido, que son las ondas estructurales de las galaxias en gran escala, están obteniendo resultados, predicciones y resultados medidas. Y la línea de las medidas va un poquitín por debajo de la predicción utilizando la constante cosmológica, constante de Einstein. Eso significa que la aceleración, la causa no es constante con el tiempo. Si es así, no está claro. Si resulta que es así, es otra cosa no explicada ni explicable. Pero los datos son los datos, siempre hay que, no puedes negar. Pero de momento está en el aire porque las discrepancias son pequeñas y las discrepancias, de las discrepancias también. Entonces es trabajo en progreso.
We have one other problem I think you hinted at, which is when we measure the Hubble constant, that's how fast the universe is expanding now, and we measure that from the cosmic microwave background, where we actually measure it 13.8 billion years ago, and then bring it to the present day, compared to just measuring it like I did in my thesis, the answers, it turns out, disagree by 8%. So not a lot, but 8%. When you're dealing with physics, which is an exact science, when you're wrong by 8%, you're wrong. You don't get partial credit in physics. Okay? So that is a mystery that we still do not understand, and it's something I'm working on to try to look at a different way to measure the distances and the Hubble constant in the nearby universe.
Entonces, hay otro problema, si no hubiera suficientes, que si mides lo que se llama la constante Hubble, que es simplemente la división entre distancia y velocidad, si se mide relativamente cerca, tienes un valor, el valor es 71 a 73. Y si lo mides utilizando el fondo cósmico, obtienes valores entre 64 y 68. La discrepancia es alrededor de 8%. Eso, si persiste con más medidas, sería grave. No puedes tragar como tal una discrepancia de 8%. Con lo cual eso se llama la tensión Hubble, se llama. Y tanto Brian como los varios colegas, sobre todo Adam Rees, que era su colega del Nobel, están investigando esto. Algunos están muy convencidos que es un problema importante y otros no se sabe todavía. Pero es otro problema del tema.
All right, I think it's always good to talk about why do we do this? Why do we do astronomy? And we do astronomy ultimately because it's interesting. But we pay for astronomy because it's useful. And I want to give you an example. We all know our iPhone. I have mine here. I'm sure most of you have one. And I want you to think about what's on an iPhone that comes from my area of astronomy and physics. We have the Wi-Fi. The Wi-Fi was developed by Australian radio astronomers looking for evaporating black holes. We have the camera. That was invented to take pictures of Jupiter on a satellite mission. We have the touch screen and the World Wide Web, which were developed at CERN as a way of communicating and working with machines. And finally, we have the GPS, which uses general relativity and super high precision clocks. Those clocks were used to do physics experiments and to run radio telescopes. And it turns out by using those clocks with general relativity, we can figure out where we are, even in the streets of Almeria, which I would not want to try without my GPS. So, astronomy, yes, it's wonderful. We think about it as a way, as a human project, but it's useful. And we should always remind ourselves that research and information are useful, even if I can't tell you what my work today will do tomorrow. It has been the way we invent things that we did not already know. And just to give you a sense of it, someone put together all of these little basic science inventions that go back into time that helped us build the iPhone. It's thousands of things.
Bueno, entonces, él dice, ¿por qué hacemos astronomía? Y la respuesta es, lo hacemos porque nos gusta y por curiosidad, puramente. Esa es la razón. Pero, obviamente, cuesta dinero, cuesta mucho dinero en algunos casos. Entonces, ¿cómo se puede justificar tal gasto? Entonces, él usó todos los rasgos de su teléfono, dijo iPhone, bueno, es que tenía que haber dicho teléfono móvil, porque no todo el mundo está vinculado con una compañía privada así. Pero todos los rasgos de nuestros teléfonos se basan en uno u otro descubrimiento, varios en astronomía, otros en física. No recuerdo todo lo que mencionó, pero uno, por ejemplo, GPS, para encontrarnos donde estamos, necesita la relatividad general, porque si no, rápidamente perdemos la precisión, muy rápidamente. Las cámaras, etcétera, se desarrollaron para obtener imágenes de Júpiter de una sonda, etcétera, etcétera, etcétera. Uno por uno nombró todos los importantes rasgos de su teléfono móvil que se deben a la ciencia básica física. Y aunque no sabemos lo que va a surgir, la ciencia básica siempre da lugar a cosas nuevas y a veces no imaginadas antes.
All right, so let's talk about our future. There are things I know. I know that the sun's nuclear engine is getting stronger and stronger, more and more powerful, and that over the next billion years, the sun will heat up and boil our oceans off. This is no reason not to work on climate change now, but it is coming. And then, in about 5 billion years, the sun will puff up to the size of where the Earth's orbit is, and the Earth will well and truly be destroyed. So that is going to happen. But for cosmology, the future of the universe, we think, is dark energy. Because dark energy is part of space itself. And as the universe gets bigger, dark energy stays as part of space, where you and we become less of us per piece of space. Space gets bigger, we stay the same. So dark energy becomes stronger and stronger over time. So eventually, you get to the point where dark energy pushes the universe apart faster and faster over time, that the universe will expand so fast that things we see today, the light will not be able to get to us. So if you think about a galaxy today putting light towards us, the light will try to come towards us, space will get bigger and bigger, and the light will not be able to keep up with the creation of space. This, turns out, is allowed in general relativity. It's not things moving faster than light, it's space being created faster than light can travel through it.
Entonces, ha entrado ahora en modo catastrófico y empieza por decir que en 1 billón de años el Sol se calentará de tal forma que los océanos se van a evaporar, etc. Y dice que eso no es ninguna razón de no trabajar en contra del cambio climático hoy. y que en 5 billones de años el Sol se va a hinchar y tragar toda la Tierra, etcétera, etcétera. Pero lo más grave es que la energía oscura va a impulsar la expansión del universo con creciente rapidez, de tal forma que llegará un momento cuando la luz de una distante galaxia no puede llegar a nosotros porque el espacio está creciendo más rápidamente que la luz puede seguir. Eso no va en contra a los principios de Einstein.
So, that leaves us with a very interesting end of the universe, but only if dark energy doesn't change. Now, 2 years ago, there was no evidence dark energy was changing. But now, we might see that it is changing. So, the future of the universe really depends on what dark energy does. If dark energy does not change, it is fixed like Einstein, then the universe will, at an ever-increasing rate, expand faster and faster, and the things I study, galaxies, will disappear. Cosmologists of the future will have nothing to look at. But if dark energy changes, maybe I get to keep my job billions of years in the future. Thank you.
Entonces, el futuro del universo depende de si la energía oscura es constante o no. Si es constante, entonces la expansión seguirá cada vez más rápido y al final las galaxias, la luz nunca va a llegar aquí y los astrónomos, en concreto los cosmólogos, no van a tener nada que hacer. Mientras que si eso cambia, puede no ser así y él va a mantener su puesto de trabajo.
Thank you.
Hola. Bueno, vamos a empezar nuestro tradicional turno de preguntas. Aquí en el Apolo y en el turno de preguntas la relatividad también falla de Einstein porque el tiempo no es relativo. El tiempo es absoluto y cuanto más rápida y concreta sea la pregunta, más gente podrá preguntar porque tenemos el tiempo tasado. Así que ya sabéis, la mecánica es levantar la mano, hacer la pregunta y cuantas más podamos hacer, mejor. A ver.
Hola, buenas noches. Maravillosa charla, ha sido espectacular. Y yo tenía una pregunta y es acerca de todas las cuestiones que ahora, digamos, son solo teoría y que falta demostrarlas, digamos, empíricamente. ¿Cuáles de ellas se consideran, digamos, que va a ser muy difícil o prácticamente imposible en un tiempo razonable de demostrar? Gracias.
Yeah, so which of these questions, difficult ones, are going to be the hardest or most difficult to solve?
So, am I on? I'm going to go here. Okay. Hello? All right. So, it's hard to know which ones will be the most difficult, but my feeling, I was asked today, if before I died, I could ask God to tell me one thing, the answer to one question. What I said is, I would want to know what dark matter is, because I think I'll understand the answer. My worry is, if I were told what dark energy is, I might not be smart enough to understand the answer. So I think dark energy is the very hard question that may require I don't know what within physics to come up with an understanding. Now, I might be wrong, but that is my gut feeling.
Entonces él dijo que alguien hoy había preguntado si antes de morir podía tener permiso de Dios de preguntar una pregunta que haría. Y él dijo, preguntaría qué es la materia oscura. ¿Y por qué eso? Porque él tiene miedo que la respuesta de qué es la energía oscura sería demasiado complicada para su propio entendimiento, con lo cual prefiero algo más seguro.
You have said, I don't know if it is a dumb question, but I'm gonna ask it anyway. You have said before that you weren't able to guess the space length using the Hubble constant. My question is if the Hubble constant does take into account the acceleration of the universe.
So, astronomers are sometimes, as we say in Australia, a bit thick. So, the Hubble constant, turns out, is not constant. It changes now. So the Hubble constant is the value of the expansion rate right now, 13.8 billion years after the Big Bang. When I look back at time, the Hubble constant changes with time. And so this is actually how we measure the accelerating universe, is we measure how the Hubble constant changes back in time.
Bueno, la constante de Hubble no es constante, es un nombre anticuada e incorrecta, siempre incorrecta. Realmente se refiere como el parámetro de Hubble. Y de hecho nos han dicho que debemos llamarlo el parámetro de Hubble-metro, pero es otra pregunta. Si mides esta expansión localmente ahora, tienes un valor. Si lo mides a distancias más grandes, obtienes otro valor. Esto es normal incluso en un universo no acelerándose, pero es la diferencia entre este otro valor y la predicción de este otro valor, que es la aceleración.
Hi, my question is about the all-ether theories, whether your data might be explained by these theories that even Einstein has some early papers on the relativity ether. And as you might know, recent developments of the old Michelson-Morley experiment have detected the wind when the Earth moves in space in a ratio of 10⁻⁵. So my question is if you can match your data with this new development of these experiments and explain the dark matter or dark energy with the old concept of ether moving continuously in spirals, creating all matter and energy.
So I'm not sure I completely understood the question, but what we do in science, whether it be one idea or another, we compare to any set of ideas that people have, okay? And so there's the model that I showed you, which is what we would say is the simplest model. But there are models that are more complex that also fit the data. But when you add complexity, it turns out it's much, much easier to fit data, especially after the fact, okay? So this model I showed you actually was calculated before we made the measurements and is simple. Thus far, we have not found, in my opinion, some people would disagree, a model that is anywhere near as simple that fits the data. And the few that do fit the data are both much more complex and I would say have issues where many physicists feel that they are contrived, that they don't represent how the physics of the universe works. But we keep testing, we keep our mind open, because that's how science makes progress. And when we see little problems, like I showed you might be appearing, maybe that will be the thing that says we need a more complex model. And one of these models might be the right one, or maybe we'll need a new one. We don't know.
Bueno, la pregunta es si un modelo similar a uno con un éter en movimiento podría explicar algunos de los fenómenos mencionados en la charla. Su respuesta es que el modelo favorecido es el más sencillo posible que se ajusta a los datos. El problema es lo siguiente: tú puedes ajustar modelos a datos de una forma magnífica con muchos parámetros variables que tú ajustas, pero eso se llama ad hoc, es decir, que la única forma realmente de hacer la cosa es predecir antes de hacer las medidas. Si predices después, eso no es tan positivo. Y con algo tan complicado como la cosmología, diferentes ideas tienen cabida, pero y discusiones, y están abiertos a diferentes ideas, pero al final tienen que cumplir las condiciones de máxima sencillez y mínima ad hoc, parámetros ajustados después para ajustar los datos.
Sí, buenas noches. Yo tengo una curiosidad. Si es verdad que el espacio se está expandiendo, ¿qué le pasa a la Vía Láctea y Andrómeda, que parece ser que van a chocar? ¿Qué fuerza es la que está impidiendo eso, la separación?
So what he said was, if it's true that space is expanding, what can you say about the predicted collision of Andromeda and the Milky Way?
So that is a detail I didn't have time to go. So it turns out space is expanding, but the space in this room is not expanding. And that's because the gravity of the Milky Way, billions of years ago, stopped the expansion of space. So our little part of the universe was expanding right after the Big Bang. There was so much gravity here, it collapsed and formed the Milky Way and the Sun and the Earth. It turns out that our part of the universe that includes the closest galaxies, including the Andromeda galaxy, there is so much gravity that Andromeda, initially moving away from us because of the expansion of space, has stopped and is being attracted to us, and Andromeda and the Milky Way will come together in about 3 or 4 billion years. There is a sphere. We don't quite know how big it is, but we think it's about 3 or 4 times the distance to Andromeda, where eventually gravity will bring that thing, all those galaxies together, and form a supergalaxy. everything beyond that will get further and further away from us over time and will, if dark energy persists, eventually disappear.
El espacio local o el espacio dentro de este teatro no está en expansión, porque la gravedad local es fuerte, suficientemente fuerte para no permitir la expansión a dominar. Y eso se aplica a un espacio que contiene las galaxias locales, que contiene la Vía Láctea y todo dentro de la Vía Láctea, Andrómeda y un grupo de galaxias que llaman un grupo local que está vinculado por gravedad y que a largo plazo se va a condensar en un objeto, supergalaxia. Pero, mientras tanto, todo el resto de las galaxias más lejos sí van a seguir alejándose. Ese es un punto que hay que tener en cuenta.
Hola, buenas tardes, gracias por la charla. Y quería aclarar, bueno, no me ha quedado la duda de si el espacio se ensancha más rápido que la velocidad de la luz, ¿por qué no se contradice con el límite de Einstein sobre la velocidad de la luz?
Okay, so if space is expanding faster than the velocity of light, why is that not in contradiction with relativity and what Einstein said about light?
So it turns out that within general relativity, things are not physically moving relative to each other. Rather, space is being created between us and distant galaxies. So there's no kinetic energy. The way general relativity accounts for things is different than special relativity. And so special relativity works in the nearby universe as predicted. But when you have the expansion of space itself, it turns out special relativity is not the way the equations work anymore. They work by general relativity. And so it does allow things to happen that seem to violate special relativity, but they don't. Another thing that happens, which will, if there are physicists in the audience, this usually gets even my friends, the physicists, upset, is energy is not conserved across the whole universe. It turns out in general relativity, something else like energy is conserved, but energy is not conserved, which, if you were thinking about creating dark energy as the universe expands, might bother you. But it turns out there's a different accounting in general relativity, and it's all consistent.
Bueno, básicamente la respuesta se basa en la diferencia entre la relatividad especial y la general. La especial maneja las cosas que no se aceleran. Y la general, en la general está permitido la creación del espacio entre galaxias, que no implica la creación de más energía. Pero en la general también la energía misma no está conservada. Eso es un poco inquietante a la física tradicional, pero es así. Y entonces cosas que aprendes en clase inicial no son así si estudias relatividad general.
Bueno, pues dar las gracias por esta conferencia tan motivadora, y si entiendo bien, las galaxias o los grupos de los cúmulos de galaxias se alejan unas de otras directamente proporcional a su distancia. Me lo imagino como un globo que le pintamos unos puntos y empezamos a inflarlo y se van alejando, y lo que queda entre ellas es espacio. Entonces supongo que habrá galaxias que no hemos visto nunca porque aún no nos ha llegado la luz, y algunas se irán perdiendo, porque alcanzarán más allá de la velocidad de la luz si esto es posible. Entonces, ¿en qué punto estamos antes de que usted pierda el trabajo?
Okay, so he says, if the expansion of space depends on distance, and some galaxies might already have gone beyond the point of no return of light, and others will go out of our view.
Yep.
How long is it before your job goes away? That's the question.
So if you look at the image behind me, 95% of the dots on that screen, the light that those galaxies emit today will never reach us. However, it turns out I get to see a lot of them between when those galaxies' light is reaching us today, because those galaxies are typically 2 or 3 billion years after the Big Bang. They're 8 or 9 billion years in the past. So it's a very slow process. So it's roughly about 1 trillion years is where very few things can be looked at. Where nothing can be seen, it's more like 10 trillion years. Now, 10 trillion years, John will tell you, is about how long the longest lived star will live. So little stars like Proxima Centauri, which is the nearest star, will live about 10 billion years. So if we were on a civilization on a star like Proxima Centauri, and we thought we were going to last until that star died, we would probably run out of things for cosmologists to do. But probably not a problem here on Earth.
Bueno, el proceso realmente, aunque es correcto, el proceso para que todas las galaxias desaparecen es relativamente largo. Él dice 10 trillones de años, pero sus trillones son nuestros billones. Entonces son 10 a la 13 años aproximadamente. Desaparencia 13. Y la vida de una estrella más pequeña al Sol, que es por ser Próximo Centauri, es mucho más larga que la vida del Sol, porque quema su fuel muy lentamente. Entonces, un planeta alrededor del Próximo Centauri a lo mejor todavía estaría con posibilidades de abrigar la vida cuando este periodo ya está completo. Entonces, da tiempo para tomar algunas cervezas.
Buenas noches. Lo mismo que el Big Bang formó un universo de materia, paralelamente pudo formarse un universo de antimateria y lo tenemos aquí ahora mismo.
Okay. So, just as our universe was formed in the Big Bang, could a Big Bang have formed an antimatter universe, an anti-universe?
So, we believe that the Big Bang formed essentially equal amounts of matter and antimatter, and for some reason, the matter we're made out of was predominant. However, imagine a universe that was the other way around. We would be made out of antimatter, but we would not call it antimatter because it would just be matter, and the stuff we're made out of would be called antimatter. So the question would be, are we allowed to have more than one universe? You know, is that a question we could conceive of? And there are many reasons to believe that perhaps the universe of all universes has many permutations of our universe with different physical laws, but we don't know. These are thoughts, but science is about taking thoughts and testing them. And we don't easily have a way to test these. So it sits in a very uncomfortable part of metaphysics. But to first order, yes, that is possible, but it doesn't mean it actually happened.
Nuestro universo, la materia que conocemos predomina porque al principio se crearon casi idénticos números de partículas y antipartículas, pero no exactamente idénticos. Había un exceso de materias normales por una parte en 1000 millones, y estas partículas somos nosotros, son la materia. Si eso puede ocurrir al revés, donde la antimateria predomina, es imaginable perfectamente. En este caso, las personas en ese universo considerarían que ellos tienen materia y nosotros somos antimateria. Pero bueno, todo este tipo de cosas son especulaciones agradables, interesantes, pero son muy difíciles de comprobar, con lo cual son muy difíciles de formar una parte real de la ciencia. Pero bueno, no son imposibles.
Bueno, tenemos que acabar. Me da mucha pena, como siempre. Me da mucha pena también que haya mucha gente que no ha podido entrar hoy a la conferencia porque ya el aforo estaba completo. De todos modos, os recuerdo una vez más que mañana se puede seguir preguntando a Brian Schmidt en la universidad, que va a dar una conferencia a las 11 y es abierta al público también. Y os espero mañana para ver a Carole Mundell. Ahora yo le daría un fuerte aplauso tanto a uno como a otro.